So I'm pleased to introduce our next speaker, Professor V. Kannan. He is a retired professor from Central University of Hyderabad and SRM University AP. His title of talk is One Area Formula in Many Ways in Old Sanskrit Books. So, and over to you, sir. Please start your talk.
Okay, thank you. Thank you, Dr. Swapnil, and thank you for other organizers also for giving me this opportunity. The old Samskrita books that I am referring to in the title are 4 books today. The most important of them is Brahmagupta's Brahmas Photas Siddhantam. The other books are Mahaviracharya's Ganita Sara Sangraham, Sridharacharya's Trishatika, and Bhaskaracharya's Leelavati. These are the 4 books that we are going to touch today. In all these 4 books, one area formula is coming. But these 4 books are describing that formula in 4 different ways. Even though the formula is one and the same, the words used are different. That's what we are going to see today. The area formula is the area of a cyclic quadrilateral. That formula has become important because for that formula, the well-known Heron's formula for the area of a triangle becomes a corollary. Because every triangle can be viewed as a quadrilateral where the fourth side is 0. Therefore, if we have a formula for the area of a quadrilateral, from that we can derive the formula for the area of a triangle. And this Brahmagupta's formula has become famous and is having this Heron's formula as a corollary of that. Only one formula we are going to discuss now, but how it is stated differently in different books, that's what we are going to appreciate. I start with a summary of today's talk. There are at least 16 important mathematical formulae that are available in old Samskrita books. For example, in today's talks themselves, Mr. Mahesh was talking about one formula that was also Brahmagupta's formula for diagonals of a cyclic quadrilateral in terms of the sides. Another speaker was talking about Bodhayana's theorem, which is also known as theorem of Pythagoras. In this way, there are many formulas that are available in these books which are at least 1000 years old. I have counted at least 16 of them, it may be more also. These formulas are taught in high schools and colleges nowadays, most of them. 1 or 2 may not be taught also. But they are taught along with a wrong information that they are of European origin. One earlier speaker, Dr. Bhatia, was saying that in NCERT books, we are making this correction. True, since a decade, we in our country are making this correction, but the same formulas are taught throughout the world. And other countries are not making this historical correction. Therefore, the world is thinking that they are of European origin. That is a different topic now. Today's topic is I'm taking one of them and we are going to discuss about that. This is about the area of triangles and the area of quadrilaterals. And the books in which we are finding them are nearly 1000 years old. First, I state the formula. Brahmagupta's formula, we can call it. What is a cyclic quadrilateral? A quadrilateral which is inscribed in a circle. That is, take 4 points on a circle with them as vertices of a quadrilateral. If a quadrilateral drawn, it is called a cyclic quadrilateral. If A, B, C, D are the sides of such a cyclic quadrilateral, then the formula for the area of that quadrilateral is given as square root of S minus A into S minus B into S minus C into S minus D where S stands for semi-perimeter, A plus B plus C plus D divided by 2. A plus B plus C plus D is called perimeter, half of it is called semi-perimeter. The same formula, I should say in the beginning that Brahmagupta did not use these symbols. Without symbols, he is stating the formula. We are going to see actual statement of Brahmagupta a little later. The same formula can be formulated differently also. Take the four quantities A plus B plus C minus D by 2, A plus B minus C plus D by 2, A minus B plus C plus D by 2, and minus A plus B plus C plus D by 2. Multiply them. That becomes the square of the area. This is another way to state the formulation. There is one reason why we are stating it two ways. In each statement, we are observing some beauty that comes out of symmetry. The four sides are A, B, C, D. And we take those, add three of them and subtract the fourth. This can be done in four different ways. Then multiply. This is a second formulation. Now, Brahmagupta puts it in a different way. He states it in a different form without these symbols also. And there are many historians who appreciate the way in which Brahmagupta is doing it. And also they are appreciating because Brahmagupta is the first in the history of the world to obtain this formula. Therefore, pioneer's credit also goes to him. First of the quote is taken from a website maintained by Kenner and Robertson. The website's name is MacTutor History of Mathematics. A short sentence there, it says, one can only marvel at this brilliant work of Brahmagupta in 628 AD. I'm having a small doubt here, it may be even 528 AD because usually we say he belongs to 6th century. Maybe I made a mistake in copying it. I will verify it later. He calls it brilliant work of Brahmagupta because the well-known Hiran's formula becomes a corollary for this. This is a generalization of that formula. Generalization to quadrilaterals from triangles. When he says one can only marvel at this, what he means is there is nothing more that one can do except admiring how 1,000 years ago this Brahmagupta was able to find it. This is about a person who is maintaining this website, the second of the two persons we mentioned in the previous slide. Edmund Frederick Robertson, FRSE, BSc, MSc, PhD. Born in the year 1943 in St. Andrews, Scotland, Professor Emeritus of Mathematics at that university. He is one of the creators of the noted MacTutor History of Mathematics archive, along with John Connor. He has written over 100 research articles, mainly in the theory of groups and semigroups. He is the author or co-author of 17 textbooks. These are only to impress upon the audience that he is a good textbook writer and also research. He is also good in research in the theory of groups and semigroups. Okay, such a person is not an ordinary person. He is appreciating Brahmagupta. Now I go to the second quote. There is one remarkable proposition, namely that which describes the area of a triangle when its three sides are known. Here also, he is referring to the quadrilateral formulation only, That is clear when from the next sentence. This does not seem to have been known to the ancient Greek geometers. The more general version of Brahmagupta is not available, not known to the Greek geometers. It is available, known only in India. The third quote is from Professor Sachau. He has translated a book of Al-Biruni. Al-Biruni lived in the 10th century, 1000 years ago. He, after visiting several countries, including India, wrote a book which, in his own language, it was translated into English by Sachau. From the translation, I am quoting. Brahmagupta occupies an important place in the history of Oriental culture. He taught astronomy to the Arabs. All these things happened 1200 or 1300 years ago. Arabs were students of Brahmagupta. Before they came to know of Ptolemy's works, he is also talking about two works in their own language, Sindh, Hind, and Al-Arkand. These works frequently occur in Arabic literature. What are they? These are the translations of Brahmagupta's works. Siddhanta, translated as Sindh, Hind. Khandakhadyaka, another treatise of Brahmagupta, translated as Al-Arkand. From this, we understand the greatness of Brahmagupta, that he had students from other countries also, and that he had written two great books, and that these books were translated in other languages also. The theorem, the one area formula that we are mentioning today, is available in the first of these two books, Brahmasputa Siddhanta. About Sachau, from whose book we quoted just now. He was a German Orientalist. He lived between 1845 and 1930. He was specializing on this single author, Al-Biruni. He wrote a translation of his book. That much is enough about him. Now I pass on to the next quote. In Edinburgh Review, this quote is taken from that, author is not known. He writes, "We confess that we did not expect to find this formula in the geometry of Hindustan, but it is there. We believe that it was unknown to the Greek geometers, this particular formula, and was, if we mistake not, published by Clavius in the 16th century, without knowing that it is available in Sanskrit books, not only of Brahmagupta but of many others. European mathematicians rediscovered it, and it was only in the 16th century that it was first published there. Look at the difference in the period. From 6th century to 16th century, we have one full 1000 years. After that, it was rediscovered in Europe. This is about Al-Biruni. Was a great scientist, a very eminent scholar, lived 1000 years ago. Here is a postal stamp in his honor. He writes about Brahmagupta. Brahmagupta was the most distinguished Indian astronomer. When he visited India, astronomy was flourishing. There were several astronomers in India who were eminent in their field. Brahmagupta did not live at that time. Brahmagupta was an older astronomer. But Brahmagupta's book was very popular. All astronomers were learning that. It was almost like a textbook for astronomy. That book contains more than 1000 Sanskrit verses. Because he was so much famous in India, this scholar, I should say that this scholar Al-Biruni directly read that book. Directly means not through translations. He was himself a Sanskrit scholar. Sometimes I admire Al-Biruni himself. He knew so many languages and so many subjects of study. Such an admirable person says that Brahmagupta was the most distinguished Indian astronomer. About Al-Biruni, a few more words. His full name, I cannot remember without seeing it here. Abu Rayhan Muhammad ibn Ahmad al-Biruni. That is his full name. But short name is al-Biruni. He was a Khwarezmian Iranic scholar. He was a polymath during the Islamic Golden Age. He was so eminent that he was called as father of comparative religion, father of modern geodesy, founder of Indology, first anthropologist, and so on. I took this information from Wikipedia. He lived in the period 973 to 1048 AD. He visited several countries. In his book itself, he is writing that he visited so many countries. He learned several languages, and it is not easy to be a scholar in too many languages, but he was. And among the languages that he was proficient with, Samskritam is also one. We have so far seen 4 quotes about Brahmagupta's greatness. This is the last that we are going to see today. Brahmagupta was one of the greatest scientists of his race and the greatest of his time. In that century, in the entire world, Brahmagupta was the greatest. His race means among Indians, Brahmagupta is the greatest scientist. Writes George Sarton in his book Introduction to the History of Science. About George Sarton itself, we are going to see a little. 1884 to 1956, he was a Belgian chemist and historian also. He is considered as the founder of the discipline of history of science. He received his PhD in mathematics in 1911. Now, part 1 of this talk has ended. I am summarizing. We saw one formula of Brahmagupta, not in Brahmagupta's words, but in the present day words. We also saw 5 quotes of appreciation for this formula. Now I am starting the part 2 of this talk. In part 2, it will be a little loaded with the Sanskrit passage itself and its meaning. We are going to the book Samskruta Siddhanta, a very famous book, more famous in those days. The passage which describes this formula, I am reading it. Bhujayogardha chatushtaya bhujo naghatat padam sukshmam. This is only half of a verse. This verse is in Arya meter. And it should be noted that all the 1008 verses of Samskruta Siddhanta are in the same meter. Bhuja means side for triangle or for quadrilateral or for any other polygon. Sides are called bhujas. Yoga means sum. Therefore, bhuja yoga will mean sum of the sides. That is what is known as perimeter. Ardha means half. Bhuja Yoga Ardha means semi-perimeter. Chatushtaya means 4 items. 4 items, 4 factors are taken using this semi-perimeter. What are the 4? He says in the next one, Bhuja Una. Una means decreased by or diminished by a side. Semi-perimeter is taken, one side is subtracted from it. That's the meaning. Now, because there are 4 sides, we will get 4 such factors, depending on which side we are subtracting. We take the semi-perimeter and subtract one side. This can happen in 4 ways. Therefore, we get 4 quantities. Next, ghata is the next word. That means product. Product of these 4 quantities, where each quantity is the difference between the semi-perimeter and one side. That product is taken. Next word is padam. The word padam is a technical term. Even though it means word, here it means it is a mathematical technical term, square root. Not only here, in many other mathematics textbooks of Sanskrit, we find that padam means square root. It is given in Sanskrit dictionaries also. Padam means square root. Now, square root is taken for this product. Last word, sukshmam. It means exactly you are getting the area. In many other places, these Sanskrit scholars are giving approximate formulas, but this formula is not like that. This is exact formula. Area of this quadrilateral is same as the square root of the product of these 4 quantities formed from the semi-perimeter in this way. We have seen the passage and its word by word meaning. Now we will see the English translation of that. It means area. It is exactly the square root of the product of 4 quantities, each of which is obtained by subtracting one side from the half perimeter. That is the translation. Now, if we use symbols, the semi-perimeter becomes A plus B plus C plus D divided by 2. And the 4 quantities mentioned by Brahmagupta are that semi-perimeter minus A is one quantity, that semi-perimeter minus B is another quantity, and so on. In this way, we get 4 quantities. We are taking the product of these 4 quantities, then taking the square root. Ready. That is exactly the area. Now we have understood Brahmagupta's area formula and also the way in which he is describing it. Now we are discussing about the way. Brahmagupta has not used symbols. Not only Brahmagupta, the other persons whom we are going to quote, Mahavira, Sridhara, Bhaskara, none of them uses symbols. But today for the area formula, if we do not use symbols and state it in this way, it looks clumsy in English. But it is not so in Sanskrit. If symbols are not there, if full words are used without symbols, there are 2 disadvantages in general. One is beauty gets lost, another is brevity gets lost. Therefore, not only for this formula, for the 16 formulas that I mentioned in the beginning and for many of them, now we will not venture to teach these formulas in our classes without symbols. We do use symbols and it is advantageous. But centuries ago in India, when these same formulas were used in textbooks and students were asked to learn them, they were learned through these verses only without symbols. Then what will happen to the beauty and brevity? We are discussing it just for 5 minutes now. Beauty is seen from the symmetry. Symmetry is more visible if symbols are used, but still the symmetry is visible in Bhuja Yoga Chatushtaya version also. What do we mean by symmetry in the formula? We mean that the area does not change if instead of A, B, C, D, I permute them and write A, C, B, D. Or I permute it in some other way and write it as D, C, B, A. Whatever permutation we take, the shape of the quadrilateral will change. That is adjacent to the side A. Instead of B, the side C is coming, means the shape is going to change. But the area does not change. This is what I see as symmetry there. More than this, it is easy to memorize the formula because of this symmetry. What happens to brevity? Brevity is by measuring the length of the formula. How do we measure the length? It is measured after typing the formula, the space taken to type that. That space taken is 16 for Brahmagupta. How do I get this 16? Bhu, Ja, Yo, in this way 16 letters. 32 in one version of the brief version of with mathematical symbols. How is this 32 calculated? If we say A plus B plus C minus D by 2, there A is occupying one space, plus is next, B is next, plus is next, C is next, and so on. In this way, if you count, totally 32 is the space occupied. In this way, the symbol-less formula of Brahmagupta is not longer in size. It uses only 16 letters. Therefore, brevity is not lost. Or there is another way to compare to see which is more brief. It is the time taken while reading out. It is 23 matras in Sanskrit. Bhu is one matra, Ja is another matra, Yo is two matras. Earlier speakers have explained how these matras are calculated, Lagu, Guru, etc. Totally, it becomes 23 matras in Brahmagupta's formula. But in the mathematical expression using symbols, it becomes more. It requires 34 matras time. Therefore, time-wise also, unexpectedly, Brahmagupta's way of describing the formula is more brief. Or we can say number of syllables there. It is almost same as the first one, 16 in Sanskrit, more than 35 in the expressions with symbols. In this way, what we have seen is Brahmagupta's formula, even though it is not using symbols, is more brief than the present version of the formula. How is it possible? It is because of some characteristics of the Sanskrit language itself. Prepositions are merged with the nouns. Compound words have hidden prepositions. Sometimes the number of letters decreases when words are joined. Because of all these reasons, when you write something in Sanskrit language, it becomes more brief. Now, this half of the part 2 is over. I'm going to make 4 remarks in mathematics. First remark is, as already mentioned, the triangle area formula becomes a corollary. Second remark is, we can verify it in particular cases where we have other formulas for areas. We are going to explain each one of it in the coming slides. The third one is, the same formula is not true for other quadrilaterals which are not cyclic. We are going to give a counter example also. Fourth is, this is maximal. What I mean is, there are cyclic quadrilaterals, also non-cyclic quadrilaterals. With the same sides ABCD, plenty of quadrilaterals can be drawn. Their areas may be different also. What Brahmagupta's formula says is, among them, all the cyclic quadrilaterals will have the same area. What I now say using the word maximal is, all the non-cyclic quadrilaterals will have less area. Area is maximal only for cyclic quadrilaterals. These remarks we will see with a little more explanation. First, I am saying what a cyclic quadrilateral is. If the 4 vertices of a quadrilateral lie on a circle, then we say that that quadrilateral is cyclic. That circle is called the circumcircle of that quadrilateral. In a cyclic quadrilateral, area is determined by the lengths of the 4 sides. What do we mean by saying determined? If the lengths are given, area is decided. The area cannot be different. It can be calculated through the lengths. Again, to explain, I'm saying for non-cyclic quadrilaterals, it is quite possible that the 4 sides have the same length, but the areas become different for different quadrilaterals. I have used the word in the 2 examples of the previous slide. Really, it is the next slide. I have pushed the previous slide as the next slide. The next slide is this slide. Here are 2 quadrilaterals. The 4 sides are 1, 1, 2, 2. If it is kept like this, with a right angle between sides 1 and 2, that is one way of drawing the quadrilateral. Then if you calculate the area becomes 2. We do not require Brahmagupta's formula to calculate this area because these are 2 right angle triangles. We can easily calculate the area. Half into base into altitude gives half into 1 into 2. 1 for each of the 2 triangles here. Total quadrilateral area is 1 plus 1 equal to 2. But now look at the figure on the right side. Here also 1, 1, 2, 2 are the side lengths. But I have put a right angle between 1 and 1. Then the area changes. Here also the area can be calculated without Brahmagupta's formula, because this again can be seen as the sum of the union of 2 triangles. One triangle, right angle triangle, where sides are 1 and 1. It is easy to calculate the area. Half into 1 into 1, it becomes half. For the other one, 3 sides are there, 2, 2, and one more side. If we calculate using Bodhayana Pythagoras theorem, it becomes root 2. Then we can calculate the area even using Brahmagupta's theorem. We can calculate the area. It becomes root 7 by 2. Calculations are done elsewhere, not included here. Therefore, total area of the quadrilateral is 1 plus root 7 divided by 2. I am observing 2 things here. First thing is these are not equal. 2 is not same as 1 plus root 7 by 2. Therefore, the area can be different even though the side lengths are same. Yeah. Another observation is 1 plus root 7 by 2 is less than this 2. Because 1 plus root 7 is less than 4. Because root 7 is less than 3. Because 3 is root 9. Root 7 is less than root 9. I'm comparing the two and finding that 2 is the bigger of these two numbers. Now I'm making a statement. It will always be so. The first one is cyclic, the second one is not cyclic. The cyclic one will always have the maximum area. The non-cyclic ones, the area will always be less. What can be the area if you ask? From 1 plus root 7 by 2 to 2, between these two numbers, if you take any other number also, it is possible to draw a quadrilateral whose area is that number. Therefore, there are plenty of answers to the single question, what is the area of a quadrilateral with sides 1, 1, 2, 2. Infinitely many areas are possible. But for cyclic one, only one answer is possible. That is number 2 here. Remember, I am not saying only one cyclic quadrilateral is there. There are plenty again. But fortunately, all of them will have the same area. Now I am going back where we left. Next, I am seeing how area of a triangle becomes a corollary for this. If ABC are the sides of a triangle, then its area is the square root of S into S minus A into S minus B into S minus C, where S is the semi-perimeter. How do I derive this from Brahmagupta's formula? I'm just putting D equal to 0. Every triangle is a degenerate cyclic quadrilateral. Just take the fourth side as 0, that's all. Then the same Brahmagupta's formula gives this formula for the area of a triangle, which is known as Heron's formula. Another is verification in known cases. A curious mind always does it. Brahmagupta has given a formula. But in some particular cases, I know another formula. Are these two coinciding? This is a very natural question. For example, if you take a rectangle, all rectangles are cyclic. That can be easily proved. For rectangles, if the sides are A, B, then using Brahmagupta's formula, I can calculate the area. And without that, for rectangle, the area is already known to me. The area is length into breadth. It is A into B. AB should be the answer. Therefore, I verify whether Brahmagupta's formula also gives the same answer AB. A little calculation is required, and it is seen that the answer is AB only. This kind of verification every student of mathematics does, because if they do not tally, then something is wrong. Now I am asking a question in general. If ABCD are the sides of a quadrilateral, can the area be expressed in terms of ABCD? I already mentioned it. Now I am mentioning it in different way. The answer is no. Just by knowing the sides, how can you tell the area? Because different quadrilaterals with same side lengths can have different areas. That's what we saw in this example also. My 4 mathematical remarks are over. Next, I make 4 remarks on the history. 4 remarks are related to 4 persons. Brahmagupta, Snell, Bhaskara, and Heron. First about Brahmagupta. Some historical remark about Brahmagupta. He has won the title Ganita Chakra Chudamani. This is an award for him. When he lived, other experts gave this title to him. The meaning of the title is Chudamani means crown jewel. Ganita Chakra means in the world of mathematics. Brahmagupta is given a title that he is the crown jewel in the world of mathematics. He was born in 598 AD. Now I agree. Previously, when I said 628 AD, that should be the correct number. His father's name is known as Jishnu. How do we know it? Because Brahmagupta himself mentions it in his book. He hails from a place called Billamala in Gujarat. He has authored two books, Brahmasputa Siddhanta and Khandakhadyaka. The former book, the first book, the book from which we have taken this passage, it consists of 24 chapters and altogether 1008 shlokas. Even mathematics problem exercises are formulated as shlokas. Therefore, some shlokas will be interesting. Some shlokas may not be interesting at all, but they are given in the verse form. Brahmagupta was bold in criticizing earlier experts because when we read in the first chapter itself, he does so. This is about history of Brahmagupta. Next is about W. Snell. Brahmagupta formula, the area formula that we are now discussing, it was rediscovered in Europe nearly 1,000 years later by W. Snell in 1619 AD. From where did I take this information? There is a book, History of Mathematics by Smith. In fact, this book is the best reference book for history of mathematics, written long ago. In that book says, W. Snell was the discoverer of this formula. That book doesn't mention Brahmagupta at all because at that time, Smith was not aware of mathematics available in Samskruta books. Therefore, to the best of his knowledge, he wrote that this formula was discovered by Snell from Netherlands in 1619 AD. Later, when so many Sanskrit books used as textbooks in India are mentioning so many formulas describing them, the history has to be rewritten. And now the scholars are agreeing that the pioneers are these Samskrita scholars. In my historical remarks, another person enters the scene, Bhaskara. Bhaskara too, that is how he is referred to in history because there were two Bhaskaras, both were mathematicians. In the bracket, I have written Astronomical Society of India. The reason is this picture of Bhaskara can always be doubted because in 12th century AD when he lived, how can one take a picture at all? One can only draw a picture seeing that person. There is a doubt whether it is the correct picture. Therefore, I am giving the reference. This picture is taken from Astronomical Society of India. What does Bhaskaracharya say about Brahmagupta's formula? He points out that the word cyclic is missing in Brahmagupta's book. We so far said that that formula is true only for cyclic quadrilaterals. How can we afford to miss the word cyclic? Then it becomes a wrong result. Probably Brahmagupta never studied non-cyclic quadrilaterals. That is, all the results mentioned about quadrilaterals in his book are about cyclic quadrilaterals only. He considered them only as quadrilaterals. This is one important remark. Among the four historical remarks, the fourth one is the name that is more popular in the world for this formula for the area of a triangle. It is sometimes called Heron's formula and some other times called Hero's formula. It is the same formula that we mentioned a little while ago. Area of a triangle and the three sides are A, B, C is the square root of S into S minus A into S minus B into S minus C, where S is semi-perimeter A plus B plus C by 2. Heron of Alexandria, that is how he is known, along with his place. Now we have made four historical remarks about Brahmagupta's formula. Next, we are going to other books. So far, we have discussed Brahmagupta's one book, Brahma Sphota Siddhanta. But there are many other Sanskrit books. At present, nearly 100 mathematics books in Sanskrit are known. We are taking now for our second book, Mahaviracharya's Ganita Sara Sangraha. There, the same formula is given in the same metrical verse, almost using the same words. Sometimes I even think, why can't he take the same verse? Brahmagupta has given a verse. Nowadays, what do we do if a formula is available in one book? When I write another textbook, I am not changing the symbols, etc. Same formula I am quoting. Similarly, Mahaviracharya could have quoted same Brahmagupta's verse, but he doesn't do so. Not only Mahaviracharya's, it seems to be a tradition. Whenever some other person writes another mathematics book, he composes his own verse for the same formula also. This verse is not very different. Bhujayutyardhachatushkati bhujahinat gunitat padam sukshmam. Same meter. Some of the words like bhuja, sukshmam, padam, etc. are same. Still some words are changed. For example, instead of yoga, yuti is used. Both mean the same. What could be the difference? Yoga means addition, yuti means sum. But in this context, both yuti and yoga mean the same thing, sum. Instead of chatushtaya, the word chatushka is used. Both mean the same. 4 quantities. Instead of vuna, the word hina is used. Both mean the same, diminished. Instead of ghata, the word gunita is used. Both mean the product, the number got by multiplying. The other words like padam, sutram, etc., they are same words. That is, making some very limited modifications, very little modifications, almost the same verse is given by Mahaviracharyas also. Now a few words about Mahavira's book. Ganita Sara Sangraha. The title means compendium of the essence of mathematics. Sara is essence, Sangraha is compendium. It was written during the reign of Amogha 9th century. Before Bhaskara, this king was of the Rashtrakuta dynasty in Karnataka state. This work comprises more than 1,130 verses in Sanskrit. Remember, this number is more than 1008, which is the number of verses in Brahma's Putta Siddhanta. A little longer. Now, for this book, many translations are available. Hindi translation is available. Telugu translation is available. English translation is available. And there are many new ideas also. He was a Jain mathematician from Mysore. Jainism was his religion. There is one reason for pointing out the religion here, because these Jain scholars have contributed a lot to subjects like mathematics. I am reading one sentence of appreciation about Mahavira. This is from John Tabak. His work is highly syncopated approach to algebra, and the emphasis in much of his text is on developing the techniques necessary to solve algebraic problems. The problem that we are now seeing is also an algebraic problem. Mahavira's book gives techniques necessary to solve these problems. This may be slightly different from earlier books. We have said so much about this formula, but the proof is not given in Brahmagupta's book. Next, I pass on to a third book, Sridharacharya's Trishatika. He belonged to 8th century AD, even prior to Mahavira, but after Brahmagupta. These persons do not call this theorem as Brahmagupta theorem. We are calling it so because we want to give the credit to the earliest one available. We call it Brahmagupta theorem. There may be a reason why these people are not calling so. The reason is, it is really not Brahmagupta's theorem also. It has been there in the tradition even before Brahmagupta. Brahmagupta also does not say that these theorems are his. They are all there in Indian tradition. Maybe from several centuries before Brahmagupta also they are passed on. Brahmagupta did only one service to this subject. Whatever is passed on from previous generations, he put them together, wrote a book consisting of 1008 verses. Therefore, it may not be correct to call it as Brahmagupta's theorem. Therefore, these persons are not giving that name. When Sridhara writes the same formula, he uses some other new words. One of them is dalam. Bhujayuti dalam chaturdha. Dalam is also a technical term which is used by Sridhara in many other contexts also. For example, Sridhara gives a formula for the sum to n terms of an arithmetic progression. In that formula also he uses the same word dalam, means half. Instead of ardham, he uses the word dalam. Tadvadhat padam ganitam. Vadha is a new word here. Vadha is also giving the meaning product. Another synonym. Instead of sukshmam, he uses the word ganitam. Ganitam means calculated. The area is calculated in this manner. Even though these minor modifications are there, the formula is the same. That you add the four sides, take the half of it, keep it in four places. One side is subtracted in each. We get four quantities. Multiply all these 4, then take the square root. This is the formula. Now, another Sanskrit passage I'm now giving. This may be the last that I'm giving today. That is, I'm going to end the talk soon. This is taken from Bhaskaracharya's Leelavati. Even though I said so much about Mahavira, Brahmagupta, etc., they are less popular than this gentleman Bhaskaracharya. Bhaskaracharya's book was, Leelavati was prescribed as a textbook pan India. Oh, in so many states, he became very popular. All the previous textbooks were replaced by Bhaskaracharya's book. One more remark on Bhaskaracharya's book is, he was not only a mathematician but also a poet. We may ask, others are also writing only in verses, mathematical formula. Why are they not called poets? Of course, they wrote poems. Still, Bhaskaracharya was a better poet because he used usually what poets will use, some decorations. One of them we are going to see in this formula itself. He uses a different meter. 1,000 years ago, people were using a single meter area for this purpose. Other meters were used for other purposes. But Bhaskaracharya broke it. He used several meters. Here is one. Sarvadoryutidalam chatussthitam bahubhirvirahitam cha tadvadhati मूलमस्फुटफलं चतुर्भुजे स्पष्टमेव मुदितं त्रिबाहुके. This is called Rathodhata meter. In books like Valmiki Ramayanam, we find it. Sarva doho. Doho is a new word he is using. Doho means doho, bhujam, bahus. All of them mean side of a polygon. Sarvadoho, take all the sides. Yuti, add them. Dalam, take the half of that. Chatuschitam, keep it in 4 places. Bahubhihi, by the sides. Virahitam, diminished by the sides. Then we get 4 quantities. Tadvadhati, take the product. Then moolam, instead of padam. All others were using the word padam. Bhaskaracharya uses the word moolam for varga moolam, square root. Asputaphalam chaturbhuje. He says, for the area of a quadrilateral, this formula is not always the best. Asputaphalam. Phalam means area. Why does he say asputam? Only for cyclic quadrilaterals it becomes correct. For non-cyclic ones, it doesn't become correct. Spashtameva muditam tribahuke. But when you take one of the 4 sides to be 0, it becomes a triangle. Then this formula becomes spashtam, exact. There is no exception. There is no triangle for which this formula will fail. But there are quadrilaterals for which this may not be true. These are his observations. Now, near the end, we have seen 4 passages in Sanskrit so far. Even though I called this third, it is really the 4th. We are finding that all these 4 are in the form of a verse. There is one reason. Students will easily memorize these verses and then remember the formula. If it is in the prose form, it is not possible. All except the last one are in Arya meter. The last one is in the meter Rathodhata. One more thing, the verses are different, though the formula is the same. Each author wants to give that formula in his own words as a verse, instead of repeating what is already given by other previous authors. These are the observations we make it here. Thank you. I am stopping here. I am suggesting some problems for further research. Cyclic quadrilaterals, we have this formula. If the number of sides is more in the polygon, pentagons or cyclic hexagons, is there a similar formula for us to think? Is it true or false that any two cyclic polygons with same side lengths are the same area? We have said for quadrilaterals it is so true. The area of any quadrilateral with sides A, B, C, D is less than or equal to the area of the cyclic one with same sides. I mentioned it as maximality theorem. This is true, but proof is required. This is true because long ago I remember to have proved it, but that proof is forgotten. Therefore, these are some problems for further research. Thank you for patiently listening. Let us appreciate Brahmagupta, Bhaskara, Mahavira, and Sridhara, and many other mathematicians of the past. Thank you.
Thank you, sir, for your wonderful talk. Now, let me stop recording.